Rishi here, and I welcome you back to our course on machine learning using Python. So we are in the clustering segment now, and in last few classes we have looked at k-means, which is one of the partitioning type of algorithm. So if you look at clustering type, it can be divided broadly in partitioning and hierarchical. Today we are going to look at another clustering algorithm which is of nature partitioning, and it is called as k-medoid or partitioning around medoid or PAM. So what we are initially try to understand is that what is this medoid, what was the motivation of that, and how do I define one. Okay, so when we want to look at motivation, we basically want to look at that what makes us move away from means. Then we look at the algorithm, we look at an illustration, we look at some of the issues and how they are solved with some of the improvements like CLARA or CLARAN. And then we'll briefly touch upon some of the research works. So this is the rough plan. All right. So let me, revise the concept of clustering quickly. So in clustering, your input is raw observations and you want to actually group these observations in their natural groups. Okay. So what is the characteristics of these natural groups? Within the group, they will be similar or there will be homogeneity, and between the clusters or between the groups, they will be different or dissimilar, or there will be heterogeneity within the groups. Okay. So one of the things that I want to draw your attention to is that here we have taken three groups, okay, but some of you might say that we will take two groups, which is also fairly acceptable. And how many clusters or how many groups to take is a very difficult design choice. Okay, now that's why clustering is inherently more difficult than classification or regression. Having said that, let's look at the issues with means. Okay, so you already know that mean is always affected by extreme values. Okay, so if you have values like 1, 2 and 300, okay, so you can see that 300 looks to be a little bit extreme. Okay, and if you calculate the arithmetic mean will be 1 plus 2 plus 300, which is 101. Okay, so it is neither close to 1 or 2 nor close to 300. Okay, and this is one of the problems, right? It is quite affected by this observation 300. Also, please note that the cluster prototype, which is the mean in this case, is not an actual observation. Okay, so the mean is 101, which is none of these original observations. Okay, so you might ask me that what is the problem with that? The problem is that many times you are maybe clustering word vectors, okay, and from each of the clusters you want to pick a representative word. Now the mean vector that you get doesn't actually represent a word. Okay, so when it is not representing a word, your purpose is defeated. Similarly, let's say you want to cluster a gene and finally you want to select some genes. Same way, the cluster mean, which is called as the centroid, is not actually a gene. Okay, so this is what these are the two problems that motivates us to look further. So we go and pick up median because we know that median is not affected by extreme values. Okay, so we are dealing with one feature. If we are dealing with one feature, then median is the middlemost value if we arrange. Okay, as example, if you look at 1, 4 and 8, 4 is the median value. All right. Now, if there are even number of observations like 1, 4, 6 and 10, the median can be thought to be 4 or 6. Okay, so both you can think as a middle value. You can take an average of 4 and 6. However, then it will be 5, and again 5 will not be an actual observation. The problem comes when you want to find median with multiple features. So how do you sort your data by two features simultaneously, right? So by both feature you cannot get a middle value. All right. So when you have such a situation, then you call the center value as a medoid. Okay. So how medoid is different from a centroid? The first and most important point is medoid is an actual observation, and you use somehow the concept of median when you calculate the medoid. So let's take a case. Let's say there are 5 observations O1, O2, O3, O4 and O5. The first step is you find the dissimilarity matrix among them. Okay. So what is a dissimilarity matrix? Dissimilarity matrix, each of the cell actually indicates the distance of the row with the column. Okay. So basically, if you look at maybe this one, O32, okay, so O32, it means that the difference between O3 and O2 is 4. How this difference is coming? You can use any standard distance metric. You can use either Euclidean or Manhattan. Okay. All right. So this is your first step. You create this dissimilarity matrix. Your next step is you find out that for each of the observation, what is the farthest distance. So what we do is we actually find out for O1 which is the furthest. So here we find that 3.2 is farthest. Here we find 4.1 is farthest. Here we find 4 is farthest, that way. Finally, we list down these max distances. And then whichever has the minimum value of that I choose as the medoid. So in this case, I choose O1 as the medoid. Okay. Now, you might be little apprehensive that should this work? So let us take this simple example that we saw for one feature. Okay, so we have these three values 1, 2 and 300. Let's try to construct this dissimilarity matrix. So dissimilarity matrix is for 1 it is going to be 0, 1 and 299. For 2 it is going to be 1, 0, 298 and for 3 it is going to be 299, 298 and 0. So here maximum value is 299, here maximum value is 298 and here maximum value is 299. So which one has minimum? 2 has got minimum. So you see that following the concept of medoid, you actually arrived at the median. However, one problem is you can understand that calculating this metric is not at all easy. Okay, so it is computationally expensive. So however rigorous this definition is, we need to look at alternative definition also. One such alternative definition is that you start by calculating the mean and then for each of the observation you find the distance of those points from the mean and then whichever is closest to the mean you call that as medoid. So simply saying medoid is the point which is closest to the mean or closest to the centroid. Okay, so in this case what we'll do is for 5 observations, maybe I will calculate the distance from the mean. So for O1, maybe this comes to 3.8. For O2, it comes to 2.5. For O3, it comes to 4. And finally, as O2 has the minimum distance, I pick this as the medoid. You may again try out with our mini example and see whether this holds or not. Okay, so let's take 1, 2 and 300 and let's calculate the distance from the mean. So the distance from the mean, as you remember, the mean is 101. So distance from 1 is 100. So distance from 2 is 99 and distance from 3 is 199. Okay. So you can still pick 2 as the median value. Okay. So that is how, you can see that these two definitions will work well in the practical case. Alright. Now let's look at the algorithm. So what we do is in PAM, we start with 2 steps basically. We have a build step. In the build step, we sequentially select k centrally located objects. Okay, so which will be initial medoids. And then what we do is that you pick 1 from this k already selected and one from n minus k if n were your original observation not selected. And you see that if you change these two, then is the cost of clustering or is the quality of clustering, becoming better? If it is becoming better, you make a swap. So you make this non-selected one as a medoid. Okay, so let's look at the algorithm and then we will discuss about quality of the cluster. So let's say we initially select k random points, okay, and then we associate each data points to the closest medoid by using any of the most common distance metrics. So these are your clusters Now for each pair of non-selected objects H, so non-selected object comes from those which are not medoid and selected object I comes from the medoids, you calculate the total swapping cost. Swapping cost means that is your cluster quality getting better by this swap, and you repeat the step unless there is no change of the medoid. Okay, so that is how this algorithm works. Okay, now coming to the question that how do you measure cluster quality? So if you remember, one of the measures was within cluster sum of squares. Okay, so basically for each of the clusters, you found the distance of all the observations in that cluster with the cluster mean. Okay, and then you sum it over all the clusters. And this you call as I said, WCSS, within cluster sum of squares. If you want to make it more general that, okay, this is like using the Euclidean norm, can I use any other distance measure? So yes, it can be genetically written with some other distance measure which denotes by D. Xj is your any observation and mi or mu I is your central. So that case you call this as a total deviance score. So between, so by the swap, your total deviance score, if it goes down, right, so then only you will make the swap. So that is the idea. Okay, now to look at this more carefully, actually there are 4 cases that can be possible when there is a probable swap. So what is the scenario? The scenario is that A and B are your original medoid and you are considering whether you will replace A by M. Okay, so if you replace A by M, what happens to the remaining point? So that is what we are going to discuss. So case 1 is that some objects are in A. So when I am saying some objects are in A, that means some objects are in the cluster denoted by the medoid A. Okay, are now near to M. Okay, so between B and M, they are nearer to M. So this will move to M. So this is case 1, so denoted by Y, which will move to M. Okay. Case 2 is some objects in A are now near to B. Okay, so they will move to B. So A is no longer a medoid. Between M and B, B is near to them, so they will move to B. Case 3 is some objects are in B and they are still close to B. So there will be no change for them. And what is case 4? Case 4 is that for some objects which are in B, M has become the nearest cluster. Hence, they will move to B. So these cases. Okay, so these are the 4 cases. So essentially for all the points, you find out that which case it falls to. And for then each of the cases, you find out the cost. Okay, the swapping cost. And then finally, for all these 4 cases, you add up the swapping cost and that gives you total swapping cost. Okay. All right. So now let's take an example and understand this further. Okay. So it turns out that actually without doing this, total or breaking up in this total 4 cases, what can be done is that in any initial configuration, I find the cost or the total deviance. Okay. And if by the swap, my total deviance goes down, then I'll move to that configuration or make the swap. If it doesn't happen, I will not do the swap. Okay. And how I will calculate the total deviance? So the formula D that I am going to use here is the Manhattan distance for ease of calculation. Okay. So let's say these are your few points given. Okay. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points over here. Okay. And the 2 points that you have chosen as the medoid are 1, 5 and 3, 3. So what we are going to do is for each of these observations, you are going to calculate the distance using this formula with the medoids. So I find the distance of 1, 5 with 1, 5. It is the medoid itself, so I get a 0. And for M2 it is 3, 3. So 1 minus 3 is 2, 5 minus 3 is 2. So I get a 4. Okay. This way I do the calculation for all the 12 observations. For a quick check, you can try finding 3, 3. And indeed, with the distance 3, 3, with the observation 3, 3, M2 is at distance 0. Okay. Now let's say I am considering a swap. And I am considering a swap with 1, 9. Okay, and there is of course no change with 3 3. So again I do the same process. Okay, and before that let me quickly tell you that how I calculate the total deviation score. So you can of course understand that uh, the observation or out of these two, okay, I will put this observation where the cost is minimum. So this 1 5 observation will go to M1, okay, and then let's pick another one. So 1 4 it will go to M2. So that is how it works out, isn't it? Okay. So the total cost of this configuration is 22 if you sum all of them. Okay. How do I get this column? So I basically take the minimum of this, okay, because if you see the total deviance score, I will of course pick the medoid which is closer to me. Okay, so my distance will be always with the closest medoid. So that's how I arrived at 22. Now let's look at this example, and if I replace 1 5 by 1 9, the cost comes to 26. Okay, so if I do a quick fact check, yes, for 1 9 the distance with the medoid 1 9 is 0, and with 3 3 of course it is 0. So I similarly calculate the minimum cost, and if I sum it up, my total deviance score comes to 26. So is this a better configuration? No, because my total cost is not going down. Now let's take another observation. So let's take now 4 4 instead of 3 3, and we repeat the calculation. A quick fact check. So indeed 4 4 for 4 4 the medoid distance has gone to 0, and for 1 5 your medoid distance is 0. So similarly you again pick the minimum of this and you sum it up, so you get 20. So now this is a valid swap. Okay, so one from the medoid and one from non-medoid is picked up. You calculate the cost difference, and if the cost goes down, then you will make the swap. So that's the basic idea. Okay, all right. Now let's look at CLARA. So PAM has a problem, as I said, that it is computationally expensive, right? So if you want to come up with that distance calculation for so many pairs, it is going to be very time consuming. So instead of that, what CLARA does is it uses sampling. So you have the entire data available with you. Instead of using all the observation, you pick a sample and you select k-medoid out of there. Okay. So and you can take multiple samples. Okay. So from multiple samples, you calculate multiple medoids. Okay. Multiple different k-medoids. Whichever k-medoids gives you the best cost or the least cost, you return that as your output. Okay, and it turns out that CLARA is computationally very fast compared with PAM or k-medoid. However, the effectiveness of CLARA depends on sample size. So let me again quickly repeat the concept of CLARA. So let's say you have 100 observations, and out of these 100 observations, you are picking 5 medoids. Okay. Now, in case of CLARA, what you are doing is maybe you are taking a sample of 20, and you may be taking 3 such samples. So 3 samples of 20. Okay. So out of these 3, you are calculating these k-medoids again. Okay, which are 5 points. So from this sample set, you get a set of medoids. You find the cost of this. Okay, using the computation that we have seen earlier. And out of this 3 configuration, whichever gives you minimum is your medoids, and that is your output. Okay. Now there was a need to further improve CLARA, and there where we see CLARAN. So CLARAN is quite different intuitively. So CLARAN thinks of the solution as a graph problem. So this is very interesting. Okay, so it thinks that the solution is a node. Okay, so what is the solution? Solution is the combination of the medoid. Okay, so combination of any of the k points out of the original observation is one of the nodes. Okay, so if there are 10 points and k equal to 2, number of possible node is 10c2, because you are basically picking any of the 2 observations and they can be the 2 medoids. So number of such possible nodes is 10c2. Okay, and if the nodes are represented by P1, P2, which are any 2 points of 10, so that is how a node will be, right? So a node will be like P1, P2, okay, if the points are like P1 to P10. Now each node is associated with cost based on the dissimilarity with all other objects. So this is what we have already seen, which is calculated by this TD score or total deviation score. Okay. Now, actually, you can think of PAM to be a graph search. Okay. So essentially, it starts from any of your nodes and then it moves to a node where the cost is going down. And you want to actually search the entire graph. You want to search the entire graph and you want to go to the node which has the least cost. So once we think in this way, right, think in terms of graph, we can understand that definitely, PAM is a very, very expensive algorithm. Okay. Now, when Clara looks at these graphs, and as I was saying that maybe we are considering 5 points out of this 10 and maybe 3 times, so 3 times we are sampling. Okay. So we are still finding the least cost node. However, instead of the graph, we are now searching on subgraphs because we are not searching on this 10 C2 node graph anymore. We are searching on this 5 C2 graph. Okay. And we choose on the basis of them. Now, let's look at CLARAN. So CLARAN, what happens is, if you think that actually in a node in a graph has k into n minus k neighbors. Okay. So what do I mean by that? So let's say your medoid is, or your solution is 1, 2. Okay. 1, 2. So which means that out of this 10 observation, I have picked the medoid or the solution as 1 and 2. Okay. Now, if you think of its neighbors, so what are neighbors? Neighbors means that at most one medoid can change at a time. Okay. So as example, P1, P2 is a neighbor of P1, P10 because P1 is not changing. Is a neighbor of P1, P3 because again P1 is not changing. Is a neighbor of P2, P10 because P2 is not changing, but not P3, P4. This should be P3 because both are changing. Okay. And what are the, how many neighbors are possible? So it is actually k into n minus k. Okay. So basically it means that for each of these two, I can replace this by n minus k neighbors, any of the remaining neighbors. Okay. So, I have replaced like 1, 3 to 110 and then 2, 3 to 210, which is 2 into 8 or 16. Okay. So CLARA, now what it does is that it actually starts from a random node, which is a random solution of medoids. And then it does a local search. So the local search means it tries to find out the best neighbor. Okay. So if it searches best neighbors, the best neighbor means it differs only by one medoid. It picks the best among that. Okay. Now, so this gives you a local minima. And then there is a parameter of CLARAN which actually tells you how many such local minima you can find by starting from a random point, random node. So whichever gives you the best result, that is the solution you get from CLARAN. And it turns out that CLARAN gives you very, very good result, both in terms of time as well as quality of solution. Okay. Now, as I said, that we will quickly look at some of the researches that are happening. Now, to tell you, as I tried to impress upon that k-means is also an area where there is a lot of research happening. Same is the case where there is lots of research happening in k-medoid. So both these researches are from 2018, 19, 20 time frame. So here what happens is they have thought of improving further, improving further than CLARAN. Okay, so this is the paper I think published in 2019. You can search by this title. So they are still working on how this cost can be brought down, and maybe you can reduce, or you can better select some of the medoids initially. So there are a lot of possibilities. And here is one more where it has been used on sentiment analysis using k-medoid clustering. Okay, for the e-commerce domain on text reviews. Okay, so they are quite being used. So I hope I could give you an understanding of how this algorithm works. And if you have any further questions, please put in comment section. We'll go through them and try to answer as best to our abilities. Thank you so much for watching this video.